Okay, good morning, everybody. I think we are ready to start for the webinar today. My name is Katharina Liebold. I'm responsible here at DYNAmore for the topic optimization. So I'm a developer of LS-Opt and also do support on LS-Opt and also LS-Task, which is our topology optimization tool. Today, Mathias, Merten and I will share the presentation, and I welcome everybody to the DYNAmore Express webinar today. If you have any questions during the webinar, please type the questions into the chat here in WebEx, and we'll collect all the questions and try to answer everything at the end of the webinar. So with that, I'll give the microphone to my colleague Mathias Merten to start with the presentation.
So, good morning also from my side. Thank you, Katharina. I also try to share my screen. Does it work? Not yet. Does it work now? Katharina, can you please?
Yes, that's
confirm?
correct presentation. It works.
Thank you. Hello everybody also from my side. My name is Mathias Merten, and at DYNAmore I'm responsible for the topic sheet forming simulation, or in general process simulation. And I also give, like nearly every DYNAmore colleague, I give also seminars, I do project work and also support. And for one of these seminars, Katharina and me prepared together for a customer. And based on such a seminar, we prepared this small example for robustness in sheet metal forming. And based on this example, we also decide to have a speech on the IDDRG conference, of course, based on published data, as we cannot share customer data for that example. And today we have time to take a deeper look on what we did, and also to take a view to the left and to the right to show the possibilities of LS-Opt for this kind of application. So with that, I would like to give you our outline for today. The first part will be presented by me, and it will be a kind of longer motivation or introduction, as I would like to present you our use case and our example on a typical industrial everyday sheet forming simulation with LS-DYNA. Your process examples maybe are different, and you may have a different workflow established in your company, but today our aim is more to show you the tools available and not to deliver a concrete solution for your issues or your questions. Therefore, we use the latest DYNAform version as a starting point. And then I will hand over to Katharina to present the metamodels and the classifier, so to say the LS-Opt workflow for our example. And also she will start with a result presentation. And then again, I will take over the presentation and finish the results and finally give a summary and an outlook, and may discuss some of the results in a bit deeper way. So let's first take a look on an industrial everyday simulation. You may have heard about DYNAform, which is our preprocessor focused for this topic. And here you can see the working user interface. And on the left, we have this feature tree, which helps us to define the process and the tools and everything. And here in the working surface, you can see the different tools we have in this process. So we have a punch, we have a binder, and we have a die. Beside or behind this user interface are several settings for LS-DYNA. For example, behind this simulation accuracy window, we have all the settings for time step, for element formulation, for number of integration points, and so on. So for a sheet forming process, we first need a blank. So in our case, it is defined based on an outline. And of course, it also needs a thickness. Here we have a thickness of 0.7 millimeter. And in case of anisotropy, we need to define the rolling angle, which is here 0 degree, which means the x direction is the main direction. We need to specify a material, and therefore we have in DYNAform already a material library available. But in addition, DYNAmore can offer you, in collaboration with the steel supplier voestalpine, a large material database consisting of roughly 100 different steels and their yield curves, their yield loci, and so on. And also, which is important for our case here, the forming limit curve is given in that database. And if you do not have this available, you can also use the well-known Keeler formula to estimate that, or the more modern approach by Abspöhl and Scholting, which is here referred as Tata Steel, but not shown on this picture. Why we need this? We would like to calculate the Formability Index, and therefore we need this FLC. And yeah, so this is the material we have for this project. If you want to use this material database or the material cards inside, you can get them for free from us. You just need to sign some kind of license agreement. So if you want to have it, just go to our homepage, to products, material cards, and write an email to our sales department, and they will do the rest, so to say. Yeah. So with that material defined, we should go on with the process. So in our case, we have a velocity controlled die. So the die is attached to the upper tool. The upper tool is the RAM in case of sheet forming processes. So here we have the forming motion, which means we have a stroke to define, and we have a velocity profile, which we prefer to do with a smooth profile, as you know. And we also do this velocity scaling, which you also know if you're familiar with metal forming in LS-DYNA. Beside that, we need to define a binder or some boundary conditions for the binder. Here we have a force-controlled binder with a stroke of 140 millimeter. As we do not take the gravity step into account, this stroke is more or less arbitrary, but we just need to take care that we do not have initial penetrations to the punch. And our general recommendation is make this as short as possible, the stroke, to save calculation time. But this can influence the result of the gravity step, so you may have different values, and yeah. In this project or in this process, we also have analytical drawbeats defined. In our case, we needed to adjust them as we changed the material from this project. So they are not the tutorial values we have originally. The analytical drawbeats in LS-DYNA are based on the contact algorithm and are defined with these kind of lines where we have so-called force factors. And one interesting thing on DYNAform is that based on these force factors and an internal drawbeat shape library, it can generate these geometric drawbeats automatically. So if I would go to this menu and press some buttons, I would get this real drawbeat shape, which can be seen here inside the mesh and also inside the CAD data. So also the surface data is generated for that, which is quite helpful if you have a complex shape you want to have inside your mesh or inside your tools. But in our case, we stick with these analytical drawbeats as they help us to save calculation time. And yeah. So with everything defined for the process, we have tools, we have blank, we have material, we have boundary conditions. All the others values are kept with the default values. We can take a look on how the process will look like. So now it should start soon. Yeah. Okay, everything like expected. The die is moving downwards to the binder and then both move together. So this is our process. And for this process, of course, we have to discuss the results as customers do it every day. There's the next slide. Here's the next slide. So For this video, I have chosen more D3 plots, and this is the result animation, which you can see quite well that we have these dynamic effects inside the blank due to the explicit time integration and the time scaling. So you see these oscillations everywhere. And additionally, what can be seen for the process, for example, here we have some wrinkles which are flattened out when the die reaches the bottom dead center. So that is also well known. So let's take a deeper look on the forming specific results. Let's take a look, for example, on the thinning. In our case, or what I prefer is to take a look on the element results, as I want to see where problems occur, and this also gives me some hints about the quality of my results, as I see the real calculation results and not the averaged values, which is often used for customer presentations or project documentations. But this averaging methodology don't tells you the true what is inside the model. So that's why I prefer this kind of viewing, because it's more honest to you. And here we can see that we have some, or the highest thinning is approximately 31% in these areas indicated by these red dots. These are points you may have expected. And so now it depends on your specifications for that material or for that kind of parts, or on your experience. What is a good value? Is 31% okay or not? In our case, we make the assumption, or we make the definition, that 35% are our limit. So in this case, we are below this limit, so this criterion would be okay. So if there would be such a traffic light, it will be on green for this criterion. So the other criterion we may take a look on is the so-called forming limit curve, or the forming limit diagram. So here you can see this curve given by the material database, and every element inside this blank is plotted inside a diagram based on its strain state. So you have the major strain, or the major principal strain, and the minor principal strain, and based on the final state, every element is plotted inside that diagram. And inside this diagram you have, of course, the limit curves, but also the curve which distinguished between thickening and thinning. So everything right of this curve is associated with thinning, and everything left of this curve is associated with thickening. So of course, in this draw-in area here under the binder, you would expect a compression zone, and therefore a pressure, and therefore a thickening. And if there is a thickening or a pressure, you could expect wrinkles, and that's why these areas are colored in these shades of red. So in our case, the whole part looks more or less green or gray. Okay, this gray is for some automotive steels where you need some minimum pre-straining to achieve a back hardening effect. You could also deactivate this one, then everything here would be green too. But everything is green, and this would be also indicating that we have a safe process. And again, I have to mention, this depends on your definitions and maybe on the specifications of your customers. For example, how to move this so-called safety margin. Here it's stayed at the default. I think it's 10% shift. But this is also defined, for example, at the standards of big German OEM, how you have to evaluate your forming results. If you do not have these standards, and then you have to rely on your own experience and decide what is a good process. For us, we stick to the defaults, and we would say, okay, this is a green part. So the other criterion we choose for this process is the Formability Index. You remember I told you that we activated inside the material library, and this button, or this option, activates for several material cards in LS-DYNA the so-called NLP option. So we have a MAT36 or 3-parameter Bala used, and this material has the option NLP, which is this one. And this activates the calculation of the formability index. And you can see it is also available for different materials. And this takes into account nonlinear strain path, as the FLC is usually obtained for linear strain path, but you do not have linear strain path in forming. Usually you have everything. And this formability index is an indicator for such cases. How does it work? There is an example inside the manual, and it is based on a conversion of the FLC. And we convert the FLC internally from the major and minor strain space to the critical equivalent strain at failure or necking via the strain ratio space. And in this space, we calculate for each time step the quotient between the current strain increment, or the increment in the equivalent strain at the current time step, and the failure strain. And then we sum up for every time step these quotients. And the sum of these quotients is the formability index. And if this value is below 1, we say this is a safe process. So again, this is also an indicator and not necessarily the truth, but it helps you to evaluate your process. In the manual, the example is a bilinear straining of a shell. And in this case, for example, you have an uniaxial pre-strain, and this may be associated with such a point in the FLC. So after this kind of forming, you will have a strain point here. And this strain point can also be translated into this space, and it may lie here. And this point is associated, you can, according to this simple formula, you can calculate the formability index and estimate it roughly of 0.6 or 60%. So this means at this point you have 60% of the formability of your material consumed for that first process. So from that you can conclude, and this is what I did with Excel in background, that for the rest of the forming you still can use 40% of the formability. So if you stay on that strain path, you can, of course, go to the FLC, which is the other 40% here. For the other strain path, you still can use 40%, but of their representative strain length. So in case of the plane strain, you have a lower point to start from, because this point is also associated with this Fi of 0.6. And from here you can see that your final point would be fail below the FLC, so your fracture occurs earlier. Different states for the biaxial path. Here you start on a higher level and you can go much further, so your failing will occur above the FLC. Please note, for each of these points, or each point has the same formability index, and based on the FLC you would underestimate, or you would estimate your material behavior wrong. And with the Fi you will know, okay, all should fail at this time. So if we take a look with this background to our part, we see here the elemental Fi value, and we see the maximum value of roughly 0.75. indicating that we used 75% of the formability, and the most forming is used here, here, and here. There are also differences how you use this criterion. Here we define the minimum layer, as this is indicated by our manual, but you may have the experience that the maximum layer is more conservative and more appropriate for your case. Then everything will shift, but we would like to present the tools and not the exact application. This is depending on your case. So in this case, all of our criterion says we will have a green part and everything will work. But of course, this is written here in very slight color. This depends on the definition of the criterion in this case. But based on this, you may start the production of the part or of the tool. What could go wrong? Well, a lot. If your looking into literature for robustness in metal forming, you may find this picture, which I have taken from a PhD work, and it shows the influencing factors of a sheet forming simulation or of a sheet forming process in general. So there is a workpiece with its geometry and tolerances. Of course, there's a material. There are the process parameters, like the tribology, which isn't constant maybe. The sequence of the part may has a role. Of course, the tool has an influence, the hardness of the tool, and if you're producing hundreds of thousands of parts, then also the wear of the tool surface play a big role. Same states for the press. The press influences also the forming result, and and on the top, all of these parameters in reality undergo some kind of scatter. And if we think back to our initial simulation example, what we have. So we have the workpiece. So this is discretized by elements. So we cannot capture, for example, the curvature perfect as we have, or as we are stick to linear elements. The same is true that the elements usually are larger than the tolerances of the part. So the tolerances here did not count or are taken into account in the simulation world. The material usually is described by one material card. And depending on your material, what you are working with, you know there are several standards. For example, for these automotive steels from the VDA, they have a very high number of criterions these materials should fulfill to be marked as, let's say, DP 800 or so. The opposite is true, for example, for structural steels, where you just have the minimum yield strength. All the other parameters can be somewhere. You just have specified a yield strength. So describing such a process for a structural steel with a material card where you just know that the yield strength is what you have or what you can buy from your supplier, this is maybe a bit tough to do simulation with that. Of course, the process is also often hard to capture in simulation, as not all effects are taken into account. For example, if you're doing cold forming with stainless steels, which are austenitic, then the austenite inside the material may undergo a phase transformation to martensite, and this is temperature dependent. And 10 or 20 Kelvin difference in the temperature can dramatically change the yield behavior of that material. And if you are producing a lot of parts, your cold forming tool also gets heated up, and therefore let's say the last part of your working day has a different temperature field than the first part of your working day, and so it is a different material you are using. And this has, of course, to be taken into account in your simulation, which I meant here with the boundary conditions. The tool usually is described by its active working surface. So we assume it usually to be a stiff part. If the working surface is stiff and does not know any deflection, we do not take into account the press. What can happen in reality? You produce a tool in, let's say, in Germany. You make the tryout in Germany and you ship the tool, for example, to any other country, for example, Poland. And there your plant or your company has there a different press. And then you need to do another tryout as the press types are different. And the elastic deflections of the tool surface caused by these different press stiffness cause, for example, production with a lot of mistakes or with a lot of rejected parts. So in research projects, this can be, or this issue is addressed since I would say 10 or 15 years, and you can use solid elements to take this into account. But you have to be aware of that your press is not the same on in every plant, for example. And finally, all of these parameters can scatter. And how we can take this into account will be presented by Katharina soon, but first it is my task to show you what kind of parameter we scatter and what data we have available. So as we are not a producing company, we have to stick to the literature, and we have to focus, or we can focus the material, as the material has a lot of published data already available. And to remind you what is a material law consisting of, usually we have an elastic law, we have the plastic flow, we have the yield criterion, and the hardening law. And we will focus on the hardening law. So every other of these aspects could be also addressed, but you need data for this. And luckily we found data for the DC04 in literature. Again, it was a PhD work, and he published based on 800 tensile tests from incoming quality control, this table and these distributions. So from that one, we know the mean value, the standard deviation, the minimum and the maximum for the yield and the tensile strength. Based on, or in his work, he proposed a Gauche type hardening, and after some rearrangement of the Gauche equation, we can obtain these both formulas. And with these values fixed, they are just a function of RPO2 and RM. And with that one, we can easily modify our LS-DYNA input generated by DYNAform. I showed before how we generate it and so on. And I just need to add these lines and modify the material card to represent this different hardening rule and use these parameters. And with the parameter expressions, I can calculate the K and P parameter of Gauche. And with that, all rework, so to say, is done and is ready to be used by LS-opt. So I think this part will be presented by Katharina now.
So I'm gonna share my presentation now, and we'll continue with the LS-opt part. So what we want to do now is we want to run a robustness analysis using our finite element model Mathias just explained in LS-opt. Of course, it would be nice if we could just run like 10,000 simulations and use the simulation results to evaluate statistics and whatever we are interested in. But since we have highly nonlinear finite element simulations, which are usually computationally expensive, we cannot afford such an amount of simulations. So the idea is, instead of using exact simulation results, we want to use approximations of the simulation results and use the approximations to evaluate statistics. We have two options here for approximations available in LS-opt. The classical approach is metamodel approximations, which are also used quite often for optimization of highly nonlinear problems. And we also have an option to use classifiers as an approximation. What's the difference between a metamodel approximation and a classifier approximation? A metamodel approximates the response value directly, so we get a simple mathematical function that describes the relation between the input parameters and the output responses, like you see here in the example. In contrast, the idea of a classifier approximation, we have support vector classification implemented in LS-opt, is not to approximate the response value, but the boundary of a constrained value, so constrained boundary. So this is something that is quite useful for reliability analysis, like what we have here. We have constraints on the responses we are interested in, and actually it's not that important to really get an approximation for the value. It's just interesting if the simulation or the parameter combination satisfies the constraints or violates the constraints. And this is what classifiers do. So classifiers can be used for constraints, for optimization, or reliability analysis, like in our case. Classifiers have definitely advantages if you have binary or discontinuous responses, because metamodel approximations are always continuous functions. We do not have binary or discontinuous responses in our example. But the other advantage of using classifiers is that we can also use it for adaptive sampling if we use LS-opt in an iterative process. And that's what we're going to use for this example. So the general idea is we use a Monte Carlo analysis, which is the methodology for robustness analysis in LS-opt. And we do not run everything in just a single iteration. We use a sequential Monte Carlo analysis, which is an iterative process. And we add additional simulation points in each iteration to improve both the metamodel and classifier accuracy, and hence also the values we evaluate on the metamodels, like the probability of failure, for example. There are two options available in LS-opt to run a sequential Monte Carlo analysis. The first one is what you see in the example in the top row here. So we just add additional simulation points for the upcoming iterations using the space filling algorithm, which means we always distribute the points in the whole design space, in the whole area we are considering for our parameters, which gives a good approximation of the metamodel in the full design space. What we're going to use now is we are more interested, or you might be more interested, in the probability of failure. So it might not be that important that we get a good metamodel approximation in the full design space, but if we want to consider the probability of failure, it's more important that the constrained boundary, what we do with classifiers, have a good approximation. So it would be nice to have a possibility to sample more points in the vicinity of the constrained boundaries. And this is what we do in LS-opt when we use adaptive sampling. And the convergence criteria we have in LS-opt here is, on the one hand, the metamodel accuracy, and on the other hand, the probability of failure that can be considered as a termination criteria for the iterative process. So our setup in LS-opt now looks like this. We run a Monte Carlo analysis, metamodel based, in a sequential, which means iterative process. We run 5 simulations per iteration and 10 iterations in total. So the idea is to improve the quality of the metamodel and the classifier by adding additional simulation points in each iteration, and hence also improve all the entities we evaluate on the metamodel, like the probability of failure, the mean values, standard deviation, and so on. To use the adaptive sampling, we first need to specify or define the classifiers. To define a classifier, we first need to extract the components we want to use from the LS-DYNA simulation results. I won't go into detail for that step. So we have interfaces to more or less all the LS-DYNA output, like D3plot and the bin-out files and entities that are available in bin-out and so on. So it's easy to extract entities like the Formability Index or the thickness reduction directly using those interfaces. And then we can use those components for the classifier definition. So you just select from the list on the right, which contains all the scalar values you defined before in your robustness analysis. And then you can specify upper bounds, lower bounds, whatever you need to specify your classifier. And that's what you see here in the screenshot of the graphical user interface of LS-Opt. So we use both the formability index and the thickness reduction to define the classifier we want to use for the adaptive sampling later on. And this is how the definition of the adaptive sampling looks like using classifiers. So as I said before, you of course have to specify the classifier before, which uses both the formability index and the thickness reduction in our case. And in this case, we do not use all the simulation points for the adaptive sampling because we are both interested in the probability of failure of our constraint values, but we are also interested in entities like the mean value and the standard deviation, so the scatter of our response, which is evaluated on the metamodel and maybe not in the vicinity of the constraint boundary. So we try to get a combination of a good quality of the metamodel everywhere in the full design space to get a good enough quality of the approximations that are evaluated just anywhere on the metamodel, and on the other hand, a good approximation of the constraint boundary. So we use 3 adaptive points and 2 space filling points in the full design space. And how many points you want to use for the adaptive sampling can be defined by the first gap and last definition here in the definition of the sampling constraint using classifiers. Then we need to define the distribution, the scatter of our parameters. This can be done in a robustness analysis by specifying noise variables. Noise variables are defined by just the name of the variable, like what you see here. And additionally, we need to specify a distribution, and here we use the values we got from the PhD thesis for the mean value and the standard deviation of the parameters. Additionally, there was also some information in that PhD thesis that there is a correlation between the 2 parameters we are using here. So this can also be specified in LS-Opt by defining a variable correlation, and the value you see here, as I said, is the value we got from literature here in this case. This is not necessary for a robustness analysis, but in this case, since we know that there is a correlation, we also used it for our setup here for our robustness analysis in LS-Opt. That's it on the setup. So now we want to look at the results. We know that we use approximations to evaluate all the statistics, so it's definitely useful to check the quality of the metamodel, since only if the quality of the metamodel is good enough, we also get good enough results for everything we evaluated on the metamodel, like mean values, standard deviation, and so on. To judge on the quality of the metamodel, the accuracy plot in LS-Opt can be used. This is the plot you see here on the left. What you see here in the plot is the computed value against the predicted response values. Computed means values extracted directly from the simulation runs, and predicted values are the same values for the same parameter combinations, but evaluated on the metamodel. And the closer the points are to the black line you see here, the better is the quality of the metamodel with respect to the points we use to calculate the metamodel. So all the points that are exactly on that black line, that means that computed and predicted is exactly the same. So we would have an exact fit of the metamodel. So in this case, the points are definitely close enough to that black line, and the quality of the metamodel is good enough. Additionally, to that plot, there are also some error measures available in LS-Opt, which are displayed in the title of the plot, what you see here, which can also be used to judge on the quality of the metamodel. Especially the square root press value you see here in the middle is interesting, since this is a value that can be used not to judge on the quality of the metamodel with respect to the points you use to calculate the metamodel, but this is an error measure to judge on the predictive capability of the metamodel. And this is definitely important, since if we evaluate the metamodel for, let's say, 10,000 points, then it's usually not the points we use to calculate the metamodel, but different parameter combinations. So we also have to make sure that the predictive capability of the metamodel is good enough, and approximately 7% Asper's value here is definitely a good enough quality of the metamodel. The next question is, we ran our robustness analysis as an iterative process. So the question is, do we get convergence here? We can use the reliability history plot to judge on the convergence of our simulations here. In this case, I show you the convergence of the probability of failure, and you see, of course, we still have slightly different values also after 5 iterations up to 10 iterations, but we are in a range where it doesn't change too much anymore. So we have convergence here for our example. We used both metamodel and classifier approximations here to get or to approximate the failure boundaries for the 2 constraints we specified. So of course, we also want to know if the results are more or less the same or totally different, which approximation might give better results than the other one. So here we compare the metamodel approximations on the left and the constraint boundaries we get using the metamodel approximations, and on the right we get the classifier approximations of the failure boundaries. The differences we see here that the metamodel has quite a few misclassified points. So points, the red points violate a constraint, the green points satisfy all the constraints, and you see that there are quite a few red points within the green area, for example, and also green points within the red area. This does not happen for the classifier, so the classifier gives a slightly better approximation of the constraint boundary for this example. Now let's have a look at the statistics of our responses. First, the thickness reduction. So what you see here on the left is the metamodel we use to evaluate all the statistics we're interested in. On the X and Y axis, the parameters are displayed, and on the Z axis, the response to thickness reduction in this case. And the points you see here are the points, the simulation points or values extracted from simulation runs we used to calculate the metamodel. So in our example, you could also directly use the metamodel to judge on the variation of the thickness reduction. Since we only have 2 parameters, we are really able to display the full metamodel in such a 3D plot. For real examples, you might have more than 2 parameters, or most of the cases we have more than 2 parameters. Then it's quite difficult, since we can never display the full metamodel, but just a 2 or 3-dimensional section of a metamodel by setting all the other parameters to fixed values. And then it's complicated in most of the cases to use the metamodel directly to judge on the variability of the response or anything else. So it's definitely useful to have other possibilities as well to display and evaluate statistical values. For example, the histogram plot, what you see on the right. So now the blue bars you see here, they are calculated using a lot of metamodel evaluations. 10,000 samples were used, evaluated on the metamodel to calculate the distribution of the thickness reduction in this case. So using those 10,000 samples, also the mean value and the standard deviation is calculated. So you get directly the values here of mean value and standard deviation, and also the probability of failure. Here I displayed both the probability of failure calculated on the metamodel approximation and also on the classifier approximation, which is quite similar for our example here. And the values, at least the mean value and the standard deviation, they are also displayed here in the scatter plot, or sorry, not in the scatter plot, in the histogram plot here. And the values are usually also displayed in the title. We don't have on that slide here. And the background is colored by feasibility. So we see that the mean value is definitely within the green area, which is good, but we have quite a large part which is within the red area, which means the constraint is violated. And this is what you also see here. If you look at the values for the probability of failure, 16% is quite a lot, which is definitely not good enough to use that model for production here in this case. One question could be, why is the probability of failure for metamodel and classifier that similar? If you look back, or if you think back on the slide we looked before, we got similar results for the metamodel and for the classifier, and also the adaptive sampling, which definitely improves the classifier approximation here in this case, also improves the quality of the metamodel in the region in the vicinity of the constraint boundary. And like this, we definitely also get a better approximation, a better metamodel approximation in that area, which also leads to better results for a probability of failure calculated on the metamodel. So no matter if you use the metamodel or classifier approximation in the end to evaluate the probability of failure and other entities, adaptive sampling is definitely useful to improve the results. The same thing for the Formability Index. I think I don't need to go into detail here because it's exactly the same. So we also see mean value, standard deviation, and probability of failure. What is a little bit different is the probability of failure is definitely lower than what we had for the thickness reduction here in our example. We now know that our parameters definitely influence our response. We have a scatter in our response by or caused by the scatter of the parameters. It might also be interesting which of the parameters influences the response more than maybe the other parameters. And we also have sensitivity measures here, or values that can be used to judge on the sensitivity of the parameters. On the top, we have the correlation coefficient. It's the linear correlation coefficient that is evaluated here in LS-Opt. And we also have the option to use a variance-based sensitivity measure, which is called stochastic contribution of the variables. And this is what you see in the plot here on the bottom. And in both cases, we get the information that the parameter RpO2 has the larger influence on that response. In this case, I just used the thickness reduction as an example to visualize those features here. In the results we looked at until now, we just looked at specific positions in our model, just scalar values. We evaluated at fixed values, at fixed positions on our model, or just anywhere on the model. If we evaluate the maximum value, for example, it might also be interesting to know where in the model our critical areas are located. So it might also be interesting to be able to visualize statistics directly on the finite element model. And LS-Opt also has a feature to do that, which is called DYNA stats for statistics. So the idea is to evaluate statistical values for all the elements, for example, or all the nodes, depending on the entity you are extracting from the D3 plot file for all the simulations we did, or again using metamodel approximations, and then use those values to again calculate statistics, but now not for a single point somewhere in our model or the maximum value, but for a full part or the whole model, for example. And then we can use those values as fringe component in LS prepost and visualize the statistical results directly on the finite element model. Here you see the first graphical user interface step of DYNA stats. You select create, which gives you that dialog. We want to get a fringe plot or define a fringe plot here. DYNA stats also has possibilities to extract histories curves from the models, but this is usually not necessary anymore to use this in DYNA stats because we also have the feature to visualize curves and also statistics of curves now directly in the LS-Opt post-processing. But the fringe plot option here definitely is a useful feature. So we select the fringe plot option. Then you get a dialog which looks like that. You see you have all the entities, all the components that are available in D3 plot available here for selection. So in our case, we might be interested in the thickness reduction, for example. Since we use adaptivity here for the LS-DYNA simulations, it's important to use that option here, follow coordinates, instead of nodes. The thing is, if you use adaptivity here in LS-DYNA and you run multiple simulations with different combinations for the parameters, you might end up with different numbers of elements of nodes, different IDs of nodes and elements, and so on for the certain simulations. And then we need a mapping that we compare the same position to the same position for the other simulations, but there might be different IDs of nodes and elements and so on. And that's what that option here does in DYNA stats. And then we need to select which type of statistics you are interested in. In this case, for example, just the statistics of the D3 plot data, and then you can select the statistic you are interested in, like the maximum value, mean value, standard deviation, and so on. And we have also the option here to use the finite element results directly to calculate statistics, or again use metamodel approximations here to evaluate the statistics for all the elements or all the nodes. Since we ran a metamodel-based robustness analysis and metamodel-based Monte Carlo analysis, it's definitely not a good idea to evaluate statistics now directly from the finite element results. The first thing is we just have 50 simulations, which is actually not enough to calculate statistics. And the other thing is that the points we use to run the simulations do not follow the distributions we specified for the parameters, but they are just distributed equally, and we use the adaptive sampling to get a good quality of the meta model and the classifier. So using the simulation results directly is not a good idea, and that's why we again use metamodel approximations to evaluate the statistics now from the 3-plot results. And with that, I give back to Mathias to present the final results and summary and outlook.
So, thank you, Katharina, for that. So let's take a look on the calculated statistics and the fringe plot of these results. We limit to the thickness or to the thinning, to the thickness reduction or to the thinning, and we have chosen to plot the maximum value. So as if you remember the first result evaluation, we have thinnings in this area. But what was interesting for me is to see that we now have here in this area also a red area, so to say. So this was not seen that strong before, but now we see the maximum overall, or we see the maximum on the metamodel for this problem. The same can be done also for the mean value, which is nearly the same, but of course a bit smaller, and which was for me quite interesting and helpful is to see the standard deviation. And honestly, I did not expect to have the highest standard deviation of the thinning in this area. I expected this area and of course also the corners, as they are the main difficulties in forming, but not in this area. So this area here cannot be indicated on the standard approach, so to say, or cannot be found by the standard approach, but with this, let's say, rather simple approach we have chosen here with given data and so on, we could have been able to identify this critical zone before the real world problems occur, so to say. And that is, I was really surprised by that, by this point here. Another thing to discuss, what data was taken to run this simulation. Here you can see in black the range of the used yield curves based on the parameters and the parameter expressions. So the used yield curves for each simulation point. And in white, you can see the yield curve used for our initial simulation based on the material library and so on. So it's definitely inside the range, but the range is really huge. So it's nearly factor 2 in the yield strength. And this may indicates, or this may gives a reason for this variance in the thinning. And from that point, or from that picture, you may conclude that, okay, it's just a simple scaling of the yield curve. But if you take a look on each yield curve on its own, you may see, for example, here that they are not the same, that there is some kind of changing in the slope and in the shape. So, and this is also what you may expect from the material science point of view, that they are not just a scaling, but they are in some way connected, and they are also connected to the yield locus and to the anisotropic values. And this was not taken into account from us, as we do not have reliable data for that available, or we were not able to find data in a short time. So this is important. So to sum up, from all these parameters may influencing the stability of your production process, we have just changed one part of it. So we just apply statistics on one part of the material card. Each of the other parameters can also undergo scatter, and you need to have data for it to make such an analysis. And so there's a lot to do. Another thing I can discuss in this format is the comparison of the metamodels, which was also quite interesting for me and was not seen by me on the first site, but on the second one it was clear and logical and could be expected. Here you can see both metamodels for the formability index on the left and for the thickness reduction on the right. And you may agree with my statement that they look very similar or even the same in most or in many areas. And if you think about the definitions of both parameters or of both responses, so the thickness reduction for a shell formulation or thickness with shells is based on the volume consistency, on the assumption of volume consistency. So it's based on the in-plane principal strains. So this is more or less a function of the in-plane straining. And if you remember the formability index, which is a function of the equivalent strain, and the equivalent strain again is a function of the principal strains, and in case of shell elements, the third direction is a function of both in-plane strains. So finally, this is also a function of the in-plane straining. So both responses we have chosen here are describing the strain state. And you can expect that the maximum value of the thinning is also connected to the maximum forming of your sheet. And therefore, it could have been expected that both look the same. But this issue or this fact shows one important thing when working with metamodels or even with more modern words like artificial intelligence and machine learning and so on, that you have to think about your parameters quite a lot. In this case, this is rather simple, but in real big data applications, this is an issue to specify your parameters. So to give an outlook, within LS-DYNA, each parameter for the simulation can be parameterized. With the parameter expression and the parameter framework, you can easily make them accessible for LS-opt. You can use this, for example, in the, I call them solver integrated preprocessing keywords like part move, which could enable, for example, the positioning of the, or a different positioning of the blank relative to the press. So some deviation inside the plane perpendicular to the working direction. Or you could iterate the initial thickness distribution of your blank. Usually we assume we have a constant thickness of, in this case, 0.7 millimeters. But from the hot and the cold rolling mill, we know that there is no constant thickness. So with that keyword, you can override this initial thickness, this initial constant thickness, with a vector and a thickness distribution, and this can also be addressed with parameters. Of course, also the friction coefficients. Usually we use constant friction, but LS-DYNA, as you know, is also capable of using friction coefficients as a function of pressure, of contact pressure and relative velocity. But you can also parameterize that and have access to it with LS-opt if you have the data available. And finally, all defined curves and many boundary related keywords have these SF or these scaling factors for the abscissae or the ordinates, or even for, they have offset values which you can use for the parameterization, and then technically easily have access to them in LS-opt. But there are some challenges. So first of all, you need a suitable simulation model of your process with all relevant effects which play a role in your process. This is the first step. Without a proper simulation model, there is no sense in making metamodels or making robustness analysis on this model. The second one is to limit yourself to relevant parameters inside your simulation, because it is not sensible to change every parameter, because you then have too much simulations and too complex models, metamodels. And the third challenge is to get a reliable range of data for your chosen parameters. In our case, we have luck, or we had luck that we were able to find good data in literature, or at least data in literature based on 800 tensile tests, but this is not possible for your press to find these data available in public. So you may need to do a lot of tests on your own to get a proper range for these parameters. So with that, I would like to close our talk today. I thank you for listening. And I forgot the video. I'm sorry. Let's take a look on that video. We need to do some forming simulation for plastics, I think. Yeah, but with that, I would like to finish our talk. And we kindly ask you to evaluate this session. I think we need to share the link inside the chat. Then you have a form which you can fill out. And your feedback is appreciated. And also, if there are some questions, we can either discuss them now, or you can ask us via our support tool. And yeah, the next DYNAmore Express webinar, I will also attend to this, and its handling, or its topic will be transferring phase transformation data from MAT 244 to MAT 245. So if you're interested in press hardening of 22 MMB5, or if you are interested in metal forming processes with phase transformations in general, or in welding, then you may attend to this webinar, as we would like to present how you can get some data for this. And yeah, so thank you for listening. There is a question. Okay. No, there's no question. There's a form. Thank you, Katharina.
Yes, I posted the link for the evaluation form in the chat. And as Mathias said, we kindly ask you to evaluate this webinar using that link here. It's not too many questions, so it won't take too much time. Thank you also from my side for listening. If there are any questions, just type it in the chat and we'll answer them. If not, I think we'll just thank you again for your attention and hopefully meet you in the next DYNAmore Express webinar. Thank you. Have a good day.
Thank you and goodbye.
Goodbye.